خب بسم الله الرحمن الرحیم. اگر چنانچه به یاد داشته باشید ما 4 جلسه به صورت مجازی در محیط ادوب کانکت قبل از تعطیلات نوروز 1400 داشتیم. 8 جلسه هم بعد از تعطیلات نوروز 1400 داشتیم. عمدتاً تو این 12 جلسه به مباحثی اشاره داشتیم که یک تناسب تنگاتنگی با فضای مجازی داشت، چون توصیفی بود هرچند که ریاضی داشت، ولی سعی کردیم متون ریاضی رو هم در محیط پاورپوینت بیاریم و انشاءالله حالا این پکیج رو هم 12 جلسه مجازی در محیط ادوب کانکت و هم جلساتی که امروز اولین جلسه حضوری هست که بنا داریم یه مقداری به ابعاد ریاضی قضیه بیشتر بپردازیم عنایت داشته باشیم و خب قطعاً نمک تعامل با حضور فیزیکی و نوشتن مطالب روی تابلو هم به درک و فهم مطلب کمک شایانی خواهد کرد و هم این هست که یک اعتماد به نفسی در مخاطب ایجاد میکنه که بدین اینجا دیگه وارد تو وارد اکویژن شروع میکنه مینویسه، به جزوه کاری نداره و چون خودش در این طور مینویسه پس ما هم باید اینطوری فکر کنیم. این پیامد ناشی از کلاس حضوری میتونه تلقی بشه، در حالی که کلاس مجازی این آبدینی نیست که فکر میکنه. آبدینی قبلا فکرشو کرده، نوشته توی پاورپوینت. این پاورپوینته که داره عرضه میکنه، فقط آبدینی از این پاورپوینت میخونه، ولی اینجا نه، چیزی از این چیزی نمیخونه، از بار دوال اکویژنز. زیبنده خواهد بود یک جمع‌بندی از مطالب 12 جلسه مجازی داشته باشیم که یه پیوستگی، یه اینتگریتی بین مطالب امروز به بعد و 12 جلسه قبل قائل بشیم. گفتیم سیاق فکری ما توی درس زمین آمار جیو استاتیستیک به تعبیر دیسکریت ماتماتیکس، ریاضیات گسسته است. برخلاف دروس مثل ریاضیات عالی مهندسی 1 یا ریاضیات عالی مهندسی 2 که ما یه معادله داریم، توی درس زمین آمار ما با معادله مواجه نیستیم. با حل معادله دیفرانسیل معمولی یا جزئی یا اینتگرالی مواجه نیستیم. خوشبختانه نوید حیات بخش کورس این هست که ما منحصراً با معادلات جبری سر کار داریم. حالا معادلات جبری هم یه حالت خاصش که بیشتر از جنس ابهاره تو معادله. What would be the problem statement from the beginning of the course up to the end? General problem statement. It might be interesting for you to connect general problem statement to continuum mechanics problem. That is, either advanced engineering mathematics 1, advanced engineering mathematics 2, or elasticity, where your approach is more or less continuum mechanics. You are working with a governing equation. Given a single partial realization of a random function. What do I mean by single partial realization of a random function? The numerical value of the state variable under consideration at the spatial location is 1. Y at S2, Y at Sn. That is what you are given. And then the question is, estimate the attribute under consideration at the point which is not sampled. This X over Y implies that you are talking about the estimated value, and these are the observed value at the point which is not sampled. Let me restate what do I mean by single, and then restate what do I mean by partial, then restate what do I mean by realization. 3 different keywords in a single sentence. Single, that means I have only one number at point S1. Precipitation, evaporation, radiation, temperature, pressure, you name it. Again, a single number at spatial location S2, and this vector implies that you may have a 1D, 2D, or 3D problem. And then Y at S1. When I say single, that means I have a single number at this point, single number at this point, single number at this point. That is what I mean by single. What do I mean by partial? I put a few dots here, and then I have to stop at some stage due to time limitation, due to labor limitation, due to money limitation. In a sense, if that is your computational domain, you are not able to observe, monitor the state variable under consideration at every point in space. You cannot put rain gauge at every point in space. You can single out. You will choose a limited number of points to monitor precipitation. Therefore, when I say partial, that means I have to be quite selective in choosing the point where I want to monitor the state variable under consideration. Once again, by single, I mean I have a single number at this point, single number at this point, single number at this point, but I pretend وانمود میکنم که I have a random variable at this point. A random variable at this point, a random variable at this point, and then the aggregation of these random variables make up a random function. In deterministic world, you will work with a number without any prefix or suffix, and then you will work with vector without prefix or suffix, and then you will work with a function. A single number, vector, function. And then when it comes to a stochastic world, you will put random in front of each term. Random number, random vector, random function. and you know how to connect random vector to random function, because we talk about the connection between random vector and random function. In a sense, random function is considered to be a vector with infinite components. A random function is considered to be a random vector with infinite components. When you're talking about a random vector, your component is finite. You can enumerate them. When it comes to random function, you still can assume that you are working with a vector, but your vector has infinite components. That is how to connect deterministic approach to a stochastic approach. Number, vector, function. Random number, random vector, random function. And even in deterministic world, when you are talking about a function is considered to be a vector with infinite components. Here, if you want to tell your audience how this problem can be connected to, say, advanced engineering mathematics 2, then instead of having a single partial realization of a random function, here you have a governing equation. The governing equation in continuum mechanics will act as a single partial realization of a random function in discrete mathematics. It's quite interesting for you to know that in advanced engineering mathematics, when you are given a governing either ordinary or partial differential equation subject to initial and boundary condition, your job, particularly numerical method, is to estimate the attribute under consideration at the point which is not sampled. Then here you are talking about the same thing. Estimate the attribute at the point which is not sampled. Which means that you're talking about the same thing. Finite element method, your approach is continuum mechanics. In geostatistics, your approach is more or less discrete mathematics. Here, we have one single random function. It may happen that we have two random functions. Say, precipitation and elevation. And then again, your job is to estimate precipitation at the point which is not sampled. Therefore, you may want to call this problem statement treating, and then you could have a situation where instead of a single random function or a single partial realization of a random function, you have two random functions or even more than two random functions. Therefore, given y1 S1I for all I from 1 to n. That is your primary variable. And then you have a secondary variable S2j, and this j could go from 1 to n. You are given a single partial realization of primary variable precipitation. You are given a single partial realization of secondary variable elevation. And then your job is to estimate primary variable precipitation at a point which is not sampled. Here, we will call this problem statement co-creation. Or you may want to call this univariate geostatistics, and then this will become multivariate geostatistics. Univariate, multivariate geostatistics. In either case, hopefully by now you will appreciate the type of approach we took to talk about these two types of problems. Here, you have to consider a few concepts. And then as soon as you specify your concept, you are ready to solve either this problem or this problem. You have to tell your audience whether your random function is to have constant versus variable mean, constant versus variable variance, known versus unknown mean, and then when it comes to support size, if the support size for observation is the same size as support size for estimation, then you have one possibility. When it happens that the support size for observation is point-wise, but the support size for estimation is block-wise, then you have to put block in front of kriging to go for block kriging instead of point kriging. As soon as you specify your assumption, whether your mean is constant or variable, variance mean constant or variable, you are given mean or not given mean, and then point versus block kriging, then you are ready to solve these two types of problems. In either case, estimated value of y at the point which is not sampled, I'm talking about this, can be written as linear combination of observation. If you denote your observation by uppercase letter, capital letter, then you should denote your estimated value by capital letter as well. If you denote your observation by lowercase letter, then you have to denote your estimated value by lowercase letter as well. There is a close connection between observation and estimation. Here you will assume that your observation is random, then you are going to get a random variable for your estimation. That is how to cast your estimator in a stochastic or probabilistic framework. That is for kriging or univariate geostatistics. When it comes to multivariate geostatistics, estimated value of primary variable at a point which is not sampled can be written as lambda 1I, which is a function of 1, 0, just like here, and then you have to put primary variable here, which is 1I, plus j from 1 to m, lambda 2j. Again, this lambda 2j will be a function of 1, 0. And then you have to put y2 s2j. This is multivariate geostatistics, and this is univariate geostatistics. Could it be possible to compare and construct your estimator with what you have in finite element? I'm quite sure that in your Master of Science, you have a chance to take a course on finite elements. Again, in finite element, you are given a computational domain. Fortunately or unfortunately, your governor equation cannot be solved analytically for a variety of reasons, and you have to estimate the attribute under consideration numerically. Please pay particular attention to how I will compare and contrast geostatistics with finite elements, where you took a course in finite elements. In finite elements, the very first task is to discretize the computational domain. What do I mean by discretizing the computational domain? By discretizing the computational domain, I mean trying to put a viewpoint here, and then that is going to be your element, finite element. And your job, your task, your objective is to estimate the attribute under consideration at this point, at this point, at this point. That is your first job. Discretize the computational domain into a number of elements. Your element could be triangular, your element could be rectangular, your element could be a typical element in finite elements. Then, here, I will assume that I have a 2D problem. You could have a 1D problem. Beam on elastic foundation. You could have a 3D problem, just like this bar here. This bar here implies that you could have a 1D, 2D, 3D problem. Here, this computational domain corresponded to 2D problem. Therefore, look at how I approximate the state variable under consideration in finite element. And then you are going to compare and contrast this estimator with this estimator. Estimated value of the state variable under consideration over a typical element E at a generic point S. This S could be a function of x and y, could be a function of x and y and z, or could be a function of x only, depending upon the number of dimensions. Approximated value of the state variable under consideration over a typical element E can be written as this tree implies that you're talking about a linear triangular element. For quadratic triangular element, Instead of 3, you are going to have 6 because your quadratic triangular element has 6 nodes. 3 here and 3 here. And then n, I, again this is going to be a function of s times phi Please try to compare and contrast this estimator in finite element with either this estimator or this estimator in geostatistics. Like Kriging, because we have one state variable here, this corresponds to this because you can easily eliminate this 0. It will become the same as that. And eliminate this 0 here, it will become generic. By the way, you can repeat this problem statement indefinitely. What does that mean? You can repeat this for all points where you have no gain range. Therefore, it's quite obvious that you can eliminate this 0 here, implying that this S is quite generic. Now, here in finite element, we will call this Ni shape function. Here, this shape function is the same as lambda. Please try to compare this to this. This lambda here and this n here act in the same way. And then this piece of I and this voice of here, this voice of Si, you can write it voice of I. Just like here, you can say this is Si. Now, in our first physical meeting, which is today, what we plan to cover is to tell you the reason why you have to specify whether this y here, or this y here, or this y here is stationary or not. It's quite important to make that assumption. What if this y here is not stationary? What would be the source of non-stationarity? It's quite obvious. If your mean is not constant, if your variance is not constant, then your random function is no longer stationary. You have a number of possibilities to have non-stationary phenomena. Possibility number 1, your mean is not constant. Then your random function is not stationary. Possibility number 2, your mean is constant, but your random function, your variance is not constant. Then you're not working with stationary phenomena, your random function is not stationary. And the third possibility is to have both of them, mean and variance, to be variable. The most complicated situation in practice, where neither your mean nor your variance is constant. And today, I would like to give you 2 examples where you have some information about your random function, and then you need to check whether your random function is stationary or not. As soon as you appreciate the nature of non-stationary phenomena, then you will compare and contrast time series analysis with the spatial series. You might remember that in my virtual classes, I argue that it's quite puzzling that you will see not even a single word like variogram in time series analysis. But when it comes to spatial series analysis, every written textbook on geostatistics work with variogram. And the reason is to tell yourself why. How could it be possible to compare and contrast measure of similarity, either covariance function or correlation function, with measure of variability, variogram function? In geostatistics, it's quite important to realize, appreciate, why do we need to resort to covariance function or variogram function. به فارسی این بسیار مهمه، اهمیت داره. این مسئله که ما میخوایم حل بکنیم، یعنی بریم مقدار تخمینگر رو در این نقطه‌ای که باران سنج نداریم، تبخیر سنج نداریم، دما سنج نداریم و میخوام بریم باران یا تبخیر یا دما رو در اون نقطه تخمین بزنیم، باید بدانیم که آمدیم این تخمینگر رو به صورت ترکیب خطی از مشاهدات نوشتیم. اینا معلومه، اینا به ما دادن. چیزی که توی این مشهور هست این که مشهور توی این بکار هست. ایلانده ها مشهور، برخلاف فرنتلمنت اینا معلوم. تو فرنتلمنت اینا معلوم. اگر گفتی مدل المان من لینیره، تکلیف این روشن. اگر گفتی که مدل من المان من کوادراتیکه، تکلیف این روشن. اینا مشهوره. خیلی جالب. یعنی تو جیواستاتیستیک اینا مشهور، اینا معلومه. تو فایننت الیمنت اینا معلومه، اینا مشهور. اینا نودال ولیو هستن، مقادیر گرهی هستن. خب این سویچ کردن داده و خواسته ها چه اتفاق افتاده اینجا که اینا معلومه، اینا مشهوره. تو جیواستاتیستیک اینا مشهوره، اینا معلومه. پاسخش توی بیان صورت مسئله است. تو صورت مسئله که ما موقع به مسئله فرنتلمنت مطرح کنیم که اینو نمیدیم. چی میدیم؟ گاورنی اکویژن رو میدیم. تو ریاضیات 2 میگیم معادله حاکمه ما اینه، برید حلش بکنید، برید جواب رو به دست بیارید. تو جواب بسته به دست بیارید، جواب بیسکریت به دست بیارید. ما جلسه آخر مجازی به طور مفصل در رابطه با measure of similarity و measure of variability صحبت کردیم. Today we would like to give you 2 examples where we find it quite informative to see under what condition a given information can be considered to be a stationary random function and under what condition your random function cannot be considered to be stationary. Stationarity can be considered to be a rule rather than an exception in a written textbook. However, when it comes to real life, when it comes to practice, non-stationary is going to be a rule rather than an exception. به فارسی موقع کتاب‌های جیواستاتیستیک رو باز می‌کنی، ایستایی قاعده است. 99% کتاب‌هایی که تو جیواستاتیستیک نوشته شده با فرض ایستایی تابع تصادفی کار رو جلو میبرن. ولی موقع وارد دنیای واقعی میشی، بارندگی، تبخیر، دما، رطوبت، whatever you name it, stationarity is not going to be a rule. It's going to be an exception. What would be the rule? The rule is to have a non-stationary phenomenon. And today I would like to give you an example where you have some information about your random function and then your job is to prove that your random function is not stationary. This question is designed to construct a random function having a linear variable. Let Wi be a set of independent random variables that take values +1 and -1 with equal probability. We are given an infinite number of random variables, say W0, W1, W2, W3, W4, W5, and so on. This index I could go from 0 to n. And then we are told that these random variables, that is W0, W1, W2, W3, are independent. What does this independency mean? That means the covariation, the covariance between Wi and Wj is 0. That is the meaning of independent random variables. Therefore, by independent random variable, given here, implies that the covariation, covariance between Wi and Wj is 0 if I is not equal to j. We should find the numerical value of covariance, which is the variance if Wi is equal to Wj. That is the meaning of independent random variable. The covariation between two random variables, two distinct, two different random variables is 0 when they are independent. And then how could it be possible to interpret this +1 and -1? It's a question of your random, it's a question of sample space. If you are given a cone, sekke, and then you are asked to flip the coin, what would be your sample space? Your sample space is either H or tail. You should get either head, hat, or tail, or whatever you name it. If you call it shear, then tail will become hat. If you flip a coin, your sample space is either H or tail. And then I would like to use this simple experiment to interpret that +1 and -1 out there. Here it says your random function, each random function, W0, W1, W2, W3, and so on, are independent. And that is the meaning of independent. And then it takes your random variable could take either +1 or -1 with equal probability. I would like to take this as an example to interpret what do I mean by that +1 and that -1. If your flipping a coin can be considered to be an experiment, and then in that experiment you have to denote your random variable by a capital letter. Here we will denote our random variable by capital W, and then the index give you various random variables. Here, if you denote your random variable by X, this X has to be a function of inherent randomness. There is no spatial variation, there is no temporal variation, and the only source of variability in this X is omega. And this omega here could be either H or T. And then you would say, this is my random variable, and this random variable will be a function of inherent randomness, omega. And this could have either +1, and this is, by the way, up to you to make this decision. If omega is equal to H, -1 if omega is equal to. Can you see how this +1 and -1 will be connected to W? Here, if I want to repeat this whole exercise for Wi, I would say Wi, this I could go from 0 to n, as a function of omega. This omega, if you are talking about a typical examples like flipping a coin, then this omega could have either H or tail because your sample space is this. And then you would say this is equal to +1 if omega is equal to, say, here you have to imagine an experiment where your sample space is considered to be 2 possibilities. A flipping a coin example has this feature where you have 2 possibilities, either H or tail. If omega is equal to whatever, if it is a flipping a coin experiment, then you would say H -1 if omega is equal to T. Let me give you another example, and that example has something to do with throwing a disc, حتی toss. If you throw a disc, then your sample space is 1, 2, 3, 4, 5, 6. Therefore, sample space when you throw a disc, toss. And then, if you denote your random variable by omega, This omega has to work on your inherent randomness. This omega could be either 1, 2, 3, 4, 5, 6. And then you have a series of number here or a series of symbolic notation here. If omega is 1, if omega is 2, is over there. Please pay attention. Please pay attention. Either here, or here, or here, you have one more sentence to make. And that is probability of x being equal to omega. This plus 1 and this minus 1 has nothing to do with the numerical value that you will put here. Here it says equal probability. What does that mean? If you are talking about either this example or this example, you have two possibilities. If you denote the probability of observing H by P1, the probability of observing T by P2, then you have two information with 1. P1 plus P2 has to be 1, and P1 has to be equal to P2 because of equal probability. Therefore, here, if you denote this by Pi, for this and this example, your Pi will become 1 over 2. But when it comes to this example, probability of x being equal to either 1, 2, or 3, or 5, or 6 will become 1 over 6. This P1, P2, P3, P4, P5, P6 has to be a number between 0 and 1. Therefore, this sentence here, Wi, a set of independent random variables. That is the meaning of random variable. And these random variables could take either plus 1 or minus 1, depending upon the nature of observation that you are making. If it is tail or head, then you will denote H by plus 1, T by minus 1. It really doesn't matter. You may want to call this minus 1, this plus 1. It really doesn't matter. The end result would not change. Hopefully by now you appreciate what does this sentence mean. And then we try to cast a random function using this random variable. A regionalized variable, I have to put a full stop here, and then I continue the problem statement by saying a regionalized variable. By regionalized variable, I mean a random function. A regionalized variable, i.e., random function. Voice of n is constructed for positive integral values of n. By summing the wi up to n. How? Y at n is equal to summation I from 0 to n wi. If you would like to create y at 1, then you have to replace this n with 1. If you want to create y at 0, then you have to replace this n with 0. Therefore, y at 0 is basically w0. When it comes to y1, y1 is equal to y0 plus y1, w. When you want to create y at 2, then y at 2 is equal to I from 0 to 2, and that will give you w0 plus w1 plus w2. That is how to create y. Here, your random function is 1d. It's 1d. And your 1d is integer, not decimal point. Therefore, your n, and this is your 0, 1, 2, 3, and so on. When your n is 0, you have only w0. And I can write it here w0. Because this I should go from 0 to 0. Will give you a single random value. When your n is 1, then y at 1 is basically w0 plus w1. Because this I should go from 0 to 1. And then when you are here, where n is equal to 2, then you should write w0 plus w1 plus w2. That is how to generate a random function from a random variable. Your random variable is w, your random function is y. Why your random function is y? Because here, if you refer to our first, if you refer to our very first lecture on geostatistics, in that lecture, we argue that every phenomenon in nature, precipitation, evaporation, radiation, temperature, pressure, soil moisture, will be a function of 5 arguments. Take precipitation. What would be these 5 arguments? The first 3 arguments is x, y, z. A spatial variation. And then T is going to be time variation because precipitation will change. And then what would be the fifth variable argument? Inherent randomness. Now, if you would like to duplicate this phenomenon here, please pay attention. Either in advanced engineering mathematics 1 or engineering mathematics 2, you have no trace of omega here. If you are in advanced engineering mathematics 2, then your governing equation is deterministic, not stochastic. If you want to correspond this general idea here to what you have here, the right way to choose this or to write this random function is to say I have n instead of space, instead of time, and then I have another argument. And the second argument has something to do with inherent randomness. Therefore, the right way to write this is to write this as y as a function of n as random. But we try to make a contract with ourselves in class saying that in general, your random function is a function of the space, time, and inherent randomness. Here, the inherent randomness is in place, and this inherent randomness has something to do with the nature of this random variable here, either one random variable or two random variable or three random variable. And then, instead of having x, y, z as being the spatial variation or t as the temporal variation, we have an integer. This integer number here acts as either spatial variation or temporal variation. What is the question? We spent how much time to define the problem? We spent almost, forget about this part, just focus on this example, almost 15 minutes or 20 minutes we spent to define the problem itself. And my suggestion, if you want to live a successful life, I would like to suggest that you spend majority of your time defining the problem itself. Forget about how to solve it. Just defining the problem. Therefore, up to this point, we try to tell the audience what is given. What will be the question? Prove that this random function is not stationary. That is the first task. Prove y sub n is not stationary. Or second order stationary. That is our first task. And then as soon as we prove that our random function is not stationary, then we are asked to prove that our random function has a linear variable. Up to this point, we try to define what is given, and now we are ready to prove these two tasks, these two questions. In fact, that is the first time that we would like to give you a typical example how to generate a random function. And then as soon as you understand how to generate a random function, the next question is to assess, evaluate the nature of this random function. First question. For a random function, please pay attention. For a random function to be considered as stationary, we have to have three conditions. Please pay attention that your random function has to have all three conditions simultaneously. If one of those three conditions are not in place, or not applicable, then your random function is no longer stationary. What are those three conditions? For a random function to be stationary, it has to be equipped with three properties. Properties number one. The expected value of random variable y at a generic point n has to be independent from n. When we are talking about the spatial series, out there we will argue that the random function is stationary if its mean is independent of spatial location. That is the first condition. Here, n acts as a spatial location. Therefore, the very first condition for stationarity is to have expected value of y at a generic point n to be independent of n. The second condition for stationarity is to have variance of y at a generic point n to be independent of n. Variance of y at a typical point n to be independent of n. That is the second condition for stationarity. The third condition for stationarity is to have covariance of y at n I at y at nj covariance. Here you have a random variable, here you have another random variable, and then if your parent random function wants to be stationary, then the covariation between these two random variables will be a function of separation lag only. We have to compute expected value, we have to compute variance, and we have to see if the third condition is applicable as well. Please pay attention. It may happen that your expected value is independent of spatial location. That's right. When it comes to variance, it may happen that your variance will be a function of independent of n. That's okay. But when it comes to covariance, your covariance is not a function of separation lag. Then your random function is no longer stationary. The very priority, I would say, أولويات, is to check this. If this property is applicable, then move to this property. It makes no sense to check this and then switch to this. The very first condition for stationarity is to have constant mean, the second is to have constant variance, and the third condition is to have covariance between two random variables to be a function of separation lag. Now, how could it be possible to check the first property? The expected value of y at the typical point n is to be independent of n. Now, if I take expectation from both sides of this equation, expected value of y at n is equal to expected value of this summation. And then, because of the linearity property of expectation, I can bring the expectation inside the summation. And then here, the expected value of wi, I have to make a decision whether wi is discrete or continuous. If you are given a random variable x, please pay attention, and then you are told that this random variable is discrete. Then the expected value of x for the case when your x is discrete is given by Could it be possible for someone to interpret this pi and this xi based on what I told out there? The expected value of x can be written as a linear combination of sample space. Here, out there, your n is 2. Why? N is 2. Because we have two possibilities for every random variable out there. Those random variables, say W0 or W1 or W2 or whatever, could take either +1 or -1. Therefore, when it comes to xi is the numerical value that your random variable could take. Therefore, I should go from 1 to 2. Then this pi is the probability that your random function could take either take or n. Again, you have it out there. This is for the case when your x is discrete. If your x is continuous, then the expected value of x can be written as this. This is how to compute the expected value of x if your x is continuous random value. If your x is discrete, then you could compute the expected value of x using this relationship. Now, this is for the general case when your random variable is denoted by x. Here you have infinite number of random variables. And for each random variable, say wi, if you want to compute expected value of wi, please pay attention. The argument for expectation is always uppercase letter. It makes no sense to write the argument of expectation in lowercase letter. Now, if you want to find the expectation, here your k should go from 1 to 2 because you have two possibilities. And then here I should write piece of k, and then I have to use a double summation for the numerical value that each w could take. I have to write w and then ik. This I corresponds to this I, and this k corresponds to this k. And then if I expand this, I should write P1, I1, plus P2, I2. And then P1 is 1 over 2 plus 1 plus 1 over 2 minus 1. And that will become 0. Because plus 1 over 2 minus 1 over 2 will cancel out. And then as soon as I manage to compute the expected value of wi, I can go ahead and compute the expected value of y at n. I have to take expectation from both sides of that equation. Expected value of y at n is equal to the expected value of this summation I simply replace this with what I have. And then because of the linearity property of this operator, I can bring it out inside. Write it as And as you can see here, the expected value of Wi is 0. Therefore, I can replace it with 0, and then the summation 0 is 0. Therefore, I am okay with the first condition. The expected value of a random function at a generic point n is constant, independent of n. That's fine. Let's move to the second property. Variance of y at n, I can replace this y at n with what I have here. We have to prove that variance of y at n, if our random function wants to be stationary, then variance of y at n has to be independent of n. Just like what we did for expectation. Now, how could it be possible to compute this variance of linear combination? Let me give you a typical formula that we repeatedly use in our previous lectures. If you have a linear combination like this, I from 1 to I, AI, XI. Xi is a random variable, and this I can go from 1 to n. Therefore, you have n random variables, and each random variable has a coefficient a1, a2, a3, a4, and n. And then if you are asked to compute the variance of this linear combination, the variance of this linear combination can be written as I from 1 to n, j from 1 to n, a sub I, a sub j, covariance of xi, xj. That is how to compute variance of linear combination. Could it be possible to use this relationship to compute the variance of this linear combination? Yes, why not? Here, your a sub I is equal to 1. Your wi is xi. By the way, if you use your knowledge in advanced linear algebra, then you can write this as A transpose or variance covariance matrix A. A quadratic form in advanced linear algebra. This A, vector A, has n components. A1, A2, up to An. And this R is the variance covariance matrix for this here. Now, if you use this relationship, you will realize that Just like what we have here, summation I from 0 to n, summation j from 0 to n, a1, a2 is 1, 1 times 1 is 1. Therefore, all we need to do is to write covariance of wi, wj. This a1 is 1, this aj is 1, and then you can eliminate it. There is no need to write. And then xi is. By the way, here your index start from 1, here your index start from 0. How could it be possible to compute this? Because we have to prove that this covariance is independent of n if we want to prove that your random function is stationary. Here we have a double summation, not a single summation. Now, please pay attention to this. Covariance of wi, wj is 0 when I is not equal to j. How could it be possible to use that information while we want to compute this double summation? One possibility is to freeze the first index and then have that summation. What does that mean? Write this as summation j from 0 to n, covariance of w0, wj, plus j from 0 to n. This n lowercase has to be the case. Covariance of w1, wj. That is how to eliminate the first summation. Plus summation j from 0 to n, covariance of wn, wj. That is how to expand the first summation and leave the second summation intact. Now, could it be possible for someone to tell me how many terms should I write here for this summation? I should write covariance of w0, w0, because j should start from 0. And then w0, w1, w0, w2, w0, w3. The only non-zero term in this summation is going to be w0 and w0. The remaining is 0. Therefore, this could be written as covariance of w0, w0. The remaining term is 0 because they are independent. Plus, when it comes to this summation, you should write w1, w0 because j should start from 0. And then w1, 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 w2, w1, w3. And then when it comes to using this information, the only single term that will remain from this is covariance of w1, w0. When it comes to this, again you have to start from 0. 0, 1, 2, 3, 4, 5, 6, 7. Every term is 0, except Wn. We can write this n term by a single summation. Summation I from 1, I from 0 to n. And then because the random variable for each argument is the same, we can replace this covariance with variance. Variance of Wi. And then our job, our task, is to compute variance of Wi. How could it be possible to compute variance of Wi? Again, we have to make a decision on whether the argument is discrete or continuous. Let me again bring your attention to a typical random variable x. If you are given x, and then you are asked to compute variance of x, you have to make a decision whether your x is discrete or continuous. If your x is discrete, then variance of x can be written as I from 1 to n, piece of I, x of I to the power of 2. That is when your random variable is discrete. If your random variable is continuous, then you have to write this as minus loss x minus mu to the power of 2 x of x x dx. In fact, here we have to write xi minus mu to the power of 2, but mu is equal to 0. Now, when it comes to this variance, let me compute this variance here and then plug it out there. Variance of W1. K from 1 to 2, piece of k, Wi k to the power of 2. In W has to be in lowercase. It will become 1 over 2 plus 1 to the power of 2 plus 1 over 2 minus 1 to the power of 2, and then it will become 1. And then when it comes here, summation I from 0 to n, 1. What would be this summation? The numerical value of this summation? What happened? We are okay with the first property, but when it comes to the second property, the variance of our random function is a function of n. Then your random function is not stationary. Your random function is not stationary. It is not stationary. And as soon as you find a property which is not applicable, you are done. There is no need to switch to the third condition for stationarity, because your variance is not constant. Your variance is variable. God willing, in our next physical meeting, I will tell you why your variance is not constant graphically and numerically as well. Therefore, we are done with the first question. Let me switch to the second question. The second question is to prove that your variogram is linear. At first, if we want to prove that our random function has linear variogram, the very first thing is to define what do I mean by variogram. Two times gamma as a function of ni nj. Can be written as variance of y at nj minus y ni. That is how to define variogram. You could replace n sub j with, say, n plus k, and then n sub I with y at n. That is how I define the argument nj and n. In a sense, if that is your direction n, and if your n is here, and then your n plus k is here, then you have to prove that your gamma can be written as a linear function of k and would not affect your computation. Your variogram will be a function of n. In a sense, your variogram could have three possibilities. And here, since we are talking about one direction, we eliminate the third possibilities. What are those three possibilities? That is something that we cover in our 12th session in virtual meeting. The first possibility is to have gamma a function of absolute location, ni and nj. The second possibility is to have gamma a function of separation vector. Here we have no vector because we are talking about gamma. The third possibility is to have gamma to be a function of separation distance. Absolute location, separation vector, separation distance. And here, since we are talking about 1D problem, therefore vector has no meaning. Here we are talking about separation distance. How could it be possible to compute this variance? And then tell the audience that gamma is a function of k itself. Fortunately, what we did here can be used effectively to compute this variance. Look at how I will go for it. I can replace this with summation I from 0 to n plus k WR. That is how we define the random function itself. Minus I from 0 to n WR. And then we have the two terms, variance of this plus variance of this minus 2 times covariance of these two summations. Variance of this summation plus variance of is minus 2 times covariance of Can you, just by using what I said here, tell me what would be the variance of the first term? Please pay attention. We have already shown that variance of yn, which we required here, variance of yn is equal to n plus 1. Therefore, we can safely replace this. It is because it is yn. And this is yn plus k. Therefore, if you have a clear insight, you would say this will become n plus k plus 1. And then when it comes to the second term, the variance will become n plus 1, just like what we have here. Now, how could it be possible to find the variance of these two random variables, the covariance between these two random variables? If I expand its summation, W0, W1, Wn, Wn plus 1, Wn plus k. That is how to expand the first summation. And then here we have to write Can you tell me the number of terms that you are going to get if you multiply this by this? Here you have how many? This is k. Let me write it in different color. Can you tell me how many terms you have here? N plus k plus 1 because of this here. Can you tell me the number of terms that you have here? And if you want to see the number of terms that you are going to get if you multiply this by this, you are going to get n plus k plus 1 and n plus 1 there. You may say, Mr. Robin, there is no multiplication between these two. There is a comma in between them. And then you are telling me to multiply them? Can you be more specific when you want to multiply this by this? Look at this relationship. Covariance
10 minutes.
Covariance between x and y can be written as expected value of x times y minus expected value of x times expected value of y. That is the general formula for covariance computation. Now, if you want to compute the covariance of this, you have to say covariance of the expected value of this times this minus expected value of this, expected value of this. But expected value of this is 0. Why? Because expected value of each term is 0. Therefore, this will cancel out, and you are left with this. Therefore, when we are talking about the covariance, we have to multiply this by this. The first step itself. This times this. Now, if you multiply W0 by W0, you are going to get something. And then W0 by W1 will give you 0 covariance because W0 and W1 are independent. Therefore, W0 times W0, W0 times becomes 0. Therefore, if I write it like this, 2n plus k plus 2. And then 2 times covariance of this times that. Because, excuse me, this should be expectation. If you multiply W0 by this, the only non-zero term is going to be W0 to the power of 2. If you multiply this W1 by this, the only non-zero term would be W1 to the power of 2. And then so on. Therefore, 2n plus k plus 2 minus 2 times. Here we have to write W0 to the power of 2, W1 to the power of 2, Wn to the power of 2. What happened to the remaining term? From n plus 1 up to n plus k. If you multiply this by this, every index is distinct, therefore the covariance will become 0. If you multiply this, and the only term that you have Wn by Wn, which is Wn to the power of 2. And then, what is the expected value of W0 to the power of 2? The expected value of W0 to the power of 2 is basically the variance of W0, the variance of W1, the variance of W, which is 1. Because we show that the variance of, where is it? Somewhere we show that, yes, here, see? This one here, variance of WR. Therefore, it will become 2n plus k plus 2 minus 2n. Because it will become 1 plus 1 plus 1 plus 1 n times. It will become n. And this 2n will cancel out with this 2n here, and you are left with k plus 2. Which means that 2 times gamma k is equal to this, then gamma k is equal to 1 over plus 1. Excuse me, because of this 0 here, I have to write this plus 1. And then this 2 times 1 will cancel out with that one, and then you are left with gamma k is equal to 1 over k. 1 over 2 times k, which is linear value. And that is what we are asked to prove. I think we are done with this example, and we ran out of time with regard to the battery of the camera. Therefore, we will stop at this point, and hopefully in our upcoming meeting we have a chance to touch on the second example as well. دست شما درد نکنه. سپاس.